Every year, a new phone or a new electric car promises a battery breakthrough, bigger capacity, faster charging, longer life. And every year, the actual improvement turns out to be modest, a slightly bigger number on a spec sheet, not the leap consumers keep expecting. That gap between promise and reality isn't a failure of engineering effort. It's a sign that batteries don't work the way most people assume. They do. Most people picture a battery as a single number, how much energy it can hold. Improve that number and everything gets better. More capacity means longer battery life, plain and simple. But a battery isn't one property. It's a small chemical system balancing 5 different goals at once: how much energy it can store, how long it lasts before wearing out, how fast it can absorb a charge, how much it costs to manufacture, and how safe it is to carry in your pocket or drive down a highway at speed. Push hard on any one of those goals, and the chemistry pushes back on at least one of the others. Understanding batteries means understanding that trade-off, not looking for the one number that fixes everything. Start with the basic mechanism, because it explains almost everything that follows. Inside a lithium-ion battery, the type used in nearly every phone, laptop, and electric car today, energy is stored by moving lithium ions back and forth between 2 electrodes through a liquid or gel electrolyte. Charging pushes ions one way. Using the device lets them flow back. The materials used for those electrodes and the chemistry of the electrolyte between them determine almost every property of the finished battery. How much energy fits in a given size, how fast ions can move without damaging anything, and how the whole system behaves as it ages. Now consider the first trade-off, the one most people have felt directly without realizing why it happens: energy density versus fast charging. To pack more energy into a battery of a given size, manufacturers use materials and structures that hold more lithium per gram. Denser electrodes, thinner separators, tighter packing between layers. That's how a phone battery keeps getting more capacity without the phone itself getting thicker every year. But denser packing also means ions have less physical room to move quickly and less tolerance for the stress of moving fast. Push too much current into a densely packed battery too quickly, and instead of neatly slotting into the electrode material, lithium can start plating onto the surface in tiny metallic deposits instead of properly absorbing. That's not just a lost efficiency problem. Over time, and especially under repeated fast charging, those deposits can grow into structures called dendrites, microscopic filaments that can eventually pierce the thin separator between the 2 electrodes and cause a short circuit. That's the core reason ultra-fast charging and maximum capacity are difficult to have simultaneously in the same battery. The very structure that lets a battery hold more energy is often the structure most easily damaged by charging it quickly. Research from the US. Department of Energy on Battery Development frames these goals explicitly as a connected set, not separate wish list items. Energy density, cycle, life, cost, safety, and charging speed all move together, and progress on one typically requires compromise on another. That same research has specifically noted that pushing energy density higher tends to reduce a battery's ability to accept fast charging safely, which is exactly the mechanism playing out at the chemical level inside. Every phone that charges more slowly, once you enable a battery health or longevity mode, that brings up the second trade-off: capacity versus lifespan. Every time a lithium-ion battery charges and discharges, the physical structure of its electrodes expands and contracts slightly, like a sponge repeatedly squeezed and released. Do that a few hundred times and it's barely noticeable. Do it thousands of times, over years of daily use, and the material slowly degrades, microscopic cracks form, some lithium becomes permanently trapped in places it can no longer usefully move from, and the battery's real-world capacity shrinks even though the battery still physically looks the same. Manufacturers can push for higher initial capacity by using more aggressive, more energy-dense chemistries. But those same chemistries often degrade faster under repeated stress, because the more tightly packed the structure, the more damage each expansion and contraction cycle does. A battery optimized purely for maximum day one capacity often isn't the one that lasts longest after 2 or 3 years of daily charging. Which is exactly why phone manufacturers, who tout huge capacity numbers on release day, are making a deliberate choice about which trade-off they're prioritizing. Not simply solving the problem outright. Then there's the trade-off most people never think about until something goes wrong: energy density versus safety. A battery is, in a very literal sense, a controlled amount of stored chemical energy sitting close to flammable materials. The entire design of a modern battery, the separator between electrodes, the specific chemical additives in the electrolyte, the shape and thickness of every internal layer, exists partly to keep that stored energy from being released all at once, instead of gradually as intended. Denser batteries pack more of that stored energy into a smaller space, which means any failure, physical damage, manufacturing defect, or a dendrite finally piercing through has a smaller margin for error before a small problem becomes a fire. This is precisely why battery recalls tend to involve devices pushing for higher capacity in a smaller form factor, and why manufacturers add safety layers, thicker separators, or cooling systems that slightly reduce the pure energy density number they could otherwise advertise as. Every safety margin engineered into a battery is capacity or charging speed that was deliberately left on the table. Cost adds a fourth constraint pulling in its own direction. Some of the materials that improve energy density, safety, or lifespan, specific cobalt or nickel-based compounds, more refined manufacturing processes, more sophisticated protective coatings are expensive, and their prices can be volatile depending on global mining and refining capacity. A manufacturer chasing the absolute best possible battery on every technical dimension would produce something too expensive for most consumer products to use at all. So real products are built around the cost ceiling first, and the energy density, safety, and lifespan numbers are optimized as much as possible within whatever that budget allows, which is part of why the battery in a budget phone and the battery in a premium electric vehicle can use meaningfully different chemistries, even though both are technically lithium-ion. And then there's weight and physical form, a constraint that looks purely mechanical, but actually loops back into all 4 other trade-offs. A smartphone battery has to be thin and light enough to fit inside a slim device that people carry all day, which limits how much protective structure and cooling can be built in. An electric vehicle battery has drastically more physical room and can support extensive cooling systems, structural reinforcement, and battery management software monitoring thousands of individual cells in real time, which is exactly why EV batteries can push energy density and fast charging further than a phone ever could, without the same safety compromise a drone or a small robot faces. The opposite problem. Every gram of battery weight directly subtracts from how much the machine can lift or how far it can travel, forcing engineers to prioritize weight over almost everything else, even at the cost of shorter range or slower charging. The same underlying battery chemistry produces very different final products, depending purely on how much physical space and cooling capacity the device around it can spare. Temperature adds a sixth pressure on top of the 5 already described, and it interacts with nearly all of them at once. Lithium-ion chemistry works best within a fairly narrow temperature range. Charge a battery when it's too cold, and the same slow ion movement problem behind. Fast charging damage gets worse, making lithium plating far more likely, even at charging speeds that would be perfectly safe at room temperature. Which is part of why phones and electric vehicles often throttle charging speed automatically in cold weather. Push a battery too hot. Whether from fast charging, heavy device use, or simply a hot car interior, and the chemical side reactions that slowly degrade capacity. Over time, accelerate significantly, shortening the battery's usable life even if nothing visibly goes wrong in the short term. Managing that temperature window requires either physical cooling systems, which add weight and cost, or software that limits performance to stay within a safe range. Which is why a phone left in direct sunlight often slows down its charging rate long before anything feels dangerously hot to the touch. Every one of the 5 core trade-offs already described gets harder to manage at the temperature extremes real devices actually encounter in daily use. This is also where battery management software becomes almost as important as the battery chemistry itself. Modern devices constantly monitor voltage, temperature, and charge rate across individual cells, making small real-time adjustments to protect the battery from the exact failure modes described above. A phone that seems to charge quickly to 80% and then noticeably slows down for the last stretch isn't malfunctioning. That slowdown is the management system deliberately avoiding the exact stress that causes long-term capacity loss, trading a few extra minutes of charging time for a battery that lasts meaningfully longer across hundreds of charge cycles. Electric vehicles take this much further, actively cooling or heating battery packs to keep them in an optimal range, regardless of outside weather, which is a major reason EV batteries can sustain both higher energy density and reasonably fast charging without the same safety margin problems a phone would face attempting the same specifications. None of this software solves the underlying chemical trade-offs. It manages them, shifting some of the burden from the raw chemistry onto continuous real-time monitoring and adjustment. It's worth comparing this to a technology people are used to seeing improve dramatically every year, because the contrast explains a lot of the frustration around battery progress. Computer chips have improved for decades by shrinking transistors and packing more of them into roughly the same space, a process that, for a long stretch, followed a fairly predictable pattern of rapid generational improvement. Batteries don't work that way. There's no equivalent of simply shrinking a component to get more performance for free. Every gain in energy density comes from finding new chemical materials or new physical structures, testing them extensively for safety and longevity, and then solving the manufacturing problem of producing them reliably at massive scale and at a price actual consumers can afford. That process is inherently slower and far less predictable than a manufacturing process built around steadily refining an existing technique. Consumers comparing battery progress to chip progress are, without realizing it, comparing two categories of engineering problem that behave in fundamentally different ways. There's a decision layer above all of this, too, that involves the entire life cycle of a battery, rather than just its performance while new. Eventually, every battery degrades to the point where it no longer meets the performance needs of its original device, even though it may still hold a meaningful amount of usable charge. Manufacturers increasingly design around that fact rather than around the impossible goal of a battery that never wears out, building packs that can be partially repaired rather than fully replaced, or designing cells so that a battery no longer suitable for a demanding electric vehicle can find a useful second life storing energy in a far less demanding stationary application. That's not a workaround for a failed technology. It's a recognition that degradation is a built-in, permanent property of the chemistry, and that good engineering plans for it rather than pretending it. A way, not because progress isn't real, but because a genuine breakthrough on one axis almost always comes with an unstated cost on another. A new material that dramatically improves energy density might also require a completely different manufacturing process that's currently far too expensive to scale. A new electrolyte that allows much faster charging might do so by sacrificing some cycle life, or requiring an entirely new safety system to manage the added risk. Solid-state batteries, one of the most discussed next-generation technologies, replace the flammable liquid electrolyte with a solid material which can meaningfully improve safety and potentially energy density at the same time. But that same solid electrolyte introduces new manufacturing challenges and new failure modes at the boundary between materials. Problems engineers are still working through at the scale needed for mass production. It's a real path forward, not a solved one, and framing it as an imminent cure-all misses exactly the kind of trade-off this entire topic is built around. This is also why battery progress looks incremental year over year instead of dramatic, and why that's actually the expected outcome rather than a disappointment. Engineers aren't failing to find one big improvement. They're carefully renegotiating 5 competing constraints at once, and every product on the market represents a deliberate set of choices about which of those constraints matters most for that particular device. A phone optimizes differently than a car. A car optimizes differently than a drone, and the battery inside each one is not an unfinished version of some ideal future battery. It's the current best answer to a genuinely difficult, multi-dimensional balancing problem that doesn't have a single correct solution, only better and worse. Trade-offs suited to what the device actually needs to do. So the next time a new device advertises a record-breaking battery number, the more useful question isn't how big that number is, it's what had to be sacrificed somewhere else in the system to get it there. Because in battery technology, there's no such thing as a free improvement, only a different set of compromises.